today's lecture is going to start with a discussion of spatial embedding, giving a little bit of a reminder of something we've actually seen before in the form of continuous space. In fact, we saw that some last time when we were talking about the relationship between networks on the one hand and network layout algorithms. So the network connectedness, the topology of the network on the one hand, so-called network type in AnyLogic, and on the other hand, the layout mechanism, how it was laid out in space and then by extension visually. So we talked some about that. We're going to just take a brief review of that. And then we're going to talk about a form of space we haven't yet seen, which is discrete space. A situation where we divide up the available area into a set of collectively exhaustive and mutually exclusive little cells. Cells that partition or tessellate the space. And agents can live within those cells and potentially hop amongst those cells. And where each cell might represent a little patch, as it were, on some surface. So we're going to take a look at a model which makes use of these discrete patches, but also makes use of another thing we haven't really seen, and kind of had mixed feelings about mixing it in, but I think it's a fine illustration of it, which is discrete time. So thus far we've been talking about things which operate in continuous time. Agents get updated, change, say they receive messages, they get infected, they recover, they die, they are born, at sort of arbitrary times in a continuous time frame. And now we're going to be talking with this model. We're going to show another alternative way of representing it, which is very common within the agent-based modeling area, which is discrete time. And this is basically a matter of discrete steps. So these agents, they move in lockstep, and they all hop together to the next step at the same time. And they hop together to the next step at the same time. So instead of having this continuous time abstraction, where things can happen as quickly as needed at certain points, say in the middle of an epidemic, and as slowly as needed during, the long winter nights of Saskatchewan. Things instead go at a very regular fixed pace. Something that's familiar from just dynamics, where models are often integrated with fixed time steps. And you can ask, what is the time step for this model? And it sort of just plods forward at that time step by time step. So we're going to be taking a look at this with a model. And we'll go into that model in quite some detail because it's a good illustration of both these concepts. So we're going to cover this first. This is all about spatial embedding. It doesn't yet have anything to do with movement of agents or situating agents, but they're not necessarily moving. Next, we're going to go on to the issue of agent mobility. How do we move these agents around the space? How do we get them to hop from cell to cell or to move continuously from one area of the space to another? So we'll take a look at different ways of achieving agent mobility. And what we'll actually find is that they interact with these. How you move the agents is a reflection of the type of space. Okay. On the one hand, you hop among these grid cells, and only one agent can be in a grid cell at a time, 1 or 0. And in the other case, you could set agents moving, and they can cross like ships in the night. If you wish them to, there's no limit on the density of agents in any one place, but they can move in a smooth sort of way according to a velocity in a certain heading. Okay, so this is an aggressive plan for today. And as time allows, I have an additional lecture planned on some elements of Java that